Alright, so this video is a continuation of the last video where I did first order Bode plots. So now I'm going to do second order Bode plots, and then hopefully, assuming this video is not too long, I'll do third order Bode plots. Okay? So let's take a second order system. I'm going to make this system critically damped just so it's easier to sort of do the math. And so I'm going to do sigma squared over s plus sigma s plus sigma. So that's a second order system. It's critically damped. The DC gain is still 1 in this case, okay? So my input is U, my output is X. I could do the whole song and dance if I wanted to, but it's two transfer functions that I'm gonna call G1 sigma over S plus sigma, and then G2 is sigma over S plus sigma. And you can kind of see you just multiply those two transfer functions together and everything's relatively good. If I factor out a sigma, I'm gonna get sigma over sigma is 1 over S times 1 over sigma plus 1. And you can do the same thing for G2, and you can see that in this case, my cutoff frequency is just sigma, okay? But I have two. I've got two cutoff frequencies, okay? So if I draw my gain in phase, my DC gain at 0 frequency is 1, and that my cutoff frequency, because it's a second order, it's not gonna be 3 dB, it's gonna be negative 6 dB. And then my roll-off is not going to be 20 dB per decade, but it's going to be 40 dB per decade. But it's going to look first order because it's two first order transfer functions multiplied together, okay? So here at 0 point, actually I don't know what this is in magnitude, but it's irrelevant. You know what, I'm just going to draw this in dB. So this is 0 dB, this is minus 6 dB, and then this slope here is minus 40 dB per decade, okay? Let's look at the phase now, all right? So the phase is going to be, let's draw it here. It's going to be 0 at a frequency of 0, and then normally at the cutoff frequency for a first order system it's minus 45, but it's two first orders put together. So at my cutoff frequency it's actually going to be minus 90, and then at infinity, it's going to hit minus 180 because it's two first order systems put together, okay? So now let's think about stability. Without doing a route table, without doing a root locus, without closing the loop, let's look at first order, or let's look at stability, okay? I'm trying to find where my magnitude is equal to 1, which is 0 dB, and, let me draw and, my phase is minus 180, okay? Well, I can immediately say from looking at this graph that this system is never going to go unstable. Okay, why? This 180 is an asymptote. It never gets there. Okay? So not only is it never going to get there, but when it does, the magnitude is nowhere near minus 1. Okay? So that means your system's not going to blow up ever. Okay? If we do, let's just go ahead and do a root locus, right? I would do 1 plus C CGH equals 0. If I assume H is 1 and C is K, I'm going to get 1 plus K sigma squared over S plus sigma, okay, equals 0. And so if I draw this on a real and imaginary axis, my open loop poles are here at minus sigma, there are two of them, and if I do the number line test, everything over here is 0, so this is not part of the root locus. Everything over here, that's 2, so that's also not part of the root locus. So that means these things have to split. They're going to go towards the asymptotes. There are 2 poles and no zeros, so the number of asymptotes is 2. The asymptote angle is 180 plus 360 L over n minus m, which is 2. So I'm going to get plus or minus 90. So I'm going to get an asymptote this way and an asymptote that way. So the poles split. So if you close the loop and increase K, if you use proportional gain, your poles are going to split at plus or minus 90, which is never going to go unstable. And that's exactly what we got here. Okay? So now let's throw a third order system on here and let's see if we can figure out what our gain and phase margins are. Okay? So let me take a picture of this guy. And then I'm going to do beacons here. Okay.
26. Okay. While it's uploading, I'm going to erase this. Okay, let's go ahead and I'm just going to make this super simple for me. I'm going to do sigma cubed, s plus sigma, s plus sigma, s plus sigma. Okay, my cutoff frequency for every single one of these is sigma, right? And if I draw gain and phase, so let's draw this really big so we can get as accurately as possible. So this is frequency. So at sigma, right, it's 3 transfer functions multiple. So my DC gain is sigma cubed over sigma cubed. So my DC gain is still 1 or 0 dB. And so at 1, I've got 0 frequency. As I increase frequency, this is going to get smaller and smaller and smaller. At my cutoff frequency, I'm not going to be minus 3 dB or 6 dB, I'm going to be minus 9 dB. So let's put let's put 0 dB here, and then let's put minus 9 dB, come over here and here, and so my graph is going to cross here, and then this is not going to be minus 20 or minus 40, it's going to be minus 60 dB per decade, okay? All right, so now let's look at the phase, all right? So I'm going to start here at 0, okay? At my first order system, at the cutoff frequency is 45, 45 times 2 is 90, 90 plus 45, because there's 3 of them, is 135. So at my cutoff frequency, so I'm going to do minus 45, minus 90, minus 135, I'm here at minus 135, okay? And then I've got 3 transfer functions back to back to back, so it's going to be 90, 180, it's going to be 270, right? And that makes sense. 135 times 2 is 270, so it's going to be 135, I don't really care what these are. This is 270, okay? And so this is going to come down this way. Actually, I guess I do care where 180 is, right? So 45, oh, so it's right here. This is 180. That makes sense, right? 45, 90, 135, 180. And then this is what, 2 something? It doesn't matter. What I care about is this guy here, because now there's a spot on the graph where my system crosses, right, 180. This is an instability point. Instability point. But remember that there's 2 requirements for instability. I first need my phase to be 180, but I need my gain to be 1, okay? And so unfortunately, that is not a gain of, it's a gain of 1 or 0 dB. That is not a gain of 1. Let me move this over here. Minus 60 dB per decade, okay? 0 dB is up here, which means that you actually have some margin, right? Again, gain margin. You have some gain margin where you can increase K, right? Because what does K do, right? How did you make this Bode plot? It was 1 plus Kg equals 0, right? And so G is your transfer function. K is going to increase the gain of your system. If you multiply your Bode plot by a gain, you're going to shift this curve up, okay? You can look at it like this. Let me draw a different color here. I'm just going to leave that over there. Your open loop transfer function, or closed loop, sorry, this is E, K, this is G. This here is in cascade, right? So if you increase K, what you're effectively doing is increasing G. You're increasing the gain of G. And so if you increase the gain of G, you're shifting this curve up. You're not the phase stays the same, but you're increasing the Bode plot up. So this means that this margin here, called GM, is how much margin you have in K before your system goes unstable. If you shift up your Bode plot by this much dB, your system is going to go unstable. That's what this means. Your phase margin is, I think in this case, infinite, or it may not be infinite. It might be, you might have a 180 degree phase margin. I'm a little hazy on the phase margin stuff. But here's the thing, if I shift up my Bode plot, my phase margin is going to be, like let me back up here. I'm gonna just say that your gain margin is where you cross 180 and then the distance between 0 dB and your graph. Your phase margin is where you cross 0 dB and the distance between your graph and here. So actually, why did I draw 45 there? Whoops. So that should have been 0 to minus 90. There you go. Okay? And so in a video after this, I'm going to show the same problem, and I'm going to show you what happens, how to calculate gain and phase from this, and then show you some closed loop stuff just to show you that this problem has 180 degree phase margin, and it's got whatever this gain margin is. Unfortunately, by hand, you can't really compute this. You have to plug in numbers to get it, but a computer can do this really easily. The thing is by looking at this, you can just look at this gain and phase plot and say, I need to be careful here, because if I increase my Bode plot to this point, I will cross this point and I will satisfy my instability and my system will go unstable. That's what this says here, okay? Now what you can also do is you could come in here, let me grab this marker over here. If I multiplied this by A, and I said AG, and it'd be KAG, what A would do is A would shift the curve up like this. It would keep the phase the same. If I shifted the curve up, now I've got a smaller gain margin, right? Because I've scaled G, I don't have as much margin in my controller. What also happens is that now my system has crossed my 0 dB boundary, and so if I come down here, now I've actually got a phase margin here. And this basically tells me if I make A shift the curve up, if my system lags by this many degrees, my system is also going to go unstable. Now, what causes lag in a system? Well, if you're tuning the controller on the computer, everything's fine. But if you put it on real hardware, well, like real circuitry takes time to compute all of the multiplication. So you could run into a situation where, say you use an Arduino for your control loop, and your control loop it's not fast enough. You know, Arduinos run at what, 16 megahertz? That's not very fast. It's possible that you're polling all of your sensors. It's possible your loop could drop down to 1 hertz. And if that much delay, that much lag is introduced into your system, if your system can't handle or absorb that much delay or that much margin, your system could also go unstable, okay? And so there is a third order system showing gain and phase. And so what I'm going to do is I'm going to do this exact same problem on the computer in Python and show you how to get gain and phase margin just by looking at the plots, okay? Hopefully this helps.